Hello! In this video, we'll be talking about the Serial Peripheral Interface, SPI. So SPI is a simple way to connect devices with just a few wires. In an SPI system, you have a master device that's communicating with one or more slave devices. The master sends out a clock signal and a data out signal, and the slave responds with a data in signal. And the master can optionally send a slave select signal to indicate which one of several slaves are chosen. So the signals are called SCK or SCLK, that's the serial clock. It's generated by the master, and there's one pulse for each bit being transmitted. MOSI, master out slave in, is the serial data coming from the master to the slave. And I really like this name because it's completely unambiguous which is which. For something like transmit data, is that with respect to the master or is it with respect to the slave? Then MISO, master in slave out, is the data coming back from the slave to the master. The name of the slave selects varies with manufacturers. Sometimes it's called slave select or chip enable or chip select. Often there's a bar over top or a B afterward or an N before it to mean not or bar, because they're usually active low to select which slave is being used. So one of the beauties of SPI is the slave hardware can just be a shift register. The master will generate the clock, and it will send this master out slave in. So before the first clock edge, it will put bit 7 on MOSI. On the rising edge of the clock, the slave will capture that bit, and the slave can also respond with its own data being sent back. Then on the next clock edge, the slave will capture bit 6. On the next clock edge, bit 5, bit 4, bit 3, bit 2, bit 1, and bit 0. So after 8 rising edges of the clock, the 8-bit shift register in the slave has received 8 bits of data, one at a time, and optionally sent back data, perhaps from the same shift register. And then you see the chip enable or slave select is low for the entire time that the data is being transmitted to enable the slave device. Here's an example of a master talking to 3 different slaves. So the serial clock comes from the master and it goes to all 3 slaves. Same way master out slave in goes to all 3 slaves. The master in slave out comes from all 3 slaves back to the master, but only one can be driving it at the time. All the others need to be tri-stating. So the master generates the slave select signals 1, 2, and 3 to indicate which slave should capture data from MOSI and respond with MISO. Here's another case of a particularly simple system where there's just one master and one slave, and so the slave select is not needed at all. It is important to remember to tie the grounds together on the system because voltages are relative to ground. If you don't have a common ground, the master and slave aren't able to communicate reliably. So as we said, the slave select is typically active low, and it might have one of a variety of names. The slave is enabled when the slave select is low. Disabling the slave device may save power consumption. For instance, if it's a data converter, turning off the slave select might turn off power to some resistors inside the data converter and save energy. So there are a variety of options of how to hook this up. If there's one slave device and you don't care about power consumption, you could just tie the slave select for that device low so it's always enabled. If there are multiple slave devices, you might use GPIO pins to turn on the desired device before the SPI transaction takes place and then turn it back off afterward. Or when there's one or more devices, some SPI controllers have some options to automatically pulse the desired slave select signal during transaction. So you program up the master to say which slave you want to talk to and it generates the pulses on the slave select pin for that slave. So in general, to set up SPI communication, first you need to decide which SPI port you're working on. So our chip, the FE310, has two SPI ports, SPI1 and SPI2, and let's use SPI1 just for the sake of concreteness. There's actually an SPI0 as well, but that one is used for communication with the program memory flash chip, so it's not available to us for peripherals. Then you need to make the pins for the SPI port into the appropriate I/O mode so they function as a special purpose rather than as a general purpose I/O. So we pick the pins for S-clock, MISO, and MOSI and put them into the I/O F0, input output function 0 mode. And if we're using the chip select, we also need to set that mode. Then we need to set the baud rate. That's how fast the clock works. And typically on a breadboard, you want to set a baud rate of a megahertz or less, because at high speed, signals tend to get distorted on a breadboard, and you might not get reliable communication. SPI is programmable. Typically, we set our clock polarity and clock phase to 0. Clock polarity of 0 means the clock is initially low and then rises each time we want to set a bit. Clock polarity of 1 means the clock is initially high and then drops. Clock phase tells us whether we want to sample the bit from MOSI on the first clock transition or the second clock transition, and if you care about this stuff, there's diagrams in the data sheet. But for most devices, the polarity and phase of 0 is correct. And for certain devices, there are other control registers you might want to set up, but typically the defaults are adequate. Alright, so now if we want to transmit data, first we take a look at the full flag in the transmit data register to see if there's space to send new data. We have to wait for that full flag to be 0 before we can send something new on the SPI. Then we write a byte into the TX data field, and the SPI will start churning away. It will make 8 clocks and send out the 8 bits of data one at a time, and meanwhile receive 8 bits of data back from the slave. Now, to look at the data we get back, we go and read the RX data register, and we look at the empty flag, which is the most significant bit of that register. If it's 1, it means received data is still empty, there is no data yet. So we keep repeating reading that register until the empty flag is 0. And at that point, we look in the RX data field, and it's got the data sent back. But when you do that read, it also takes that data out of the queue coming back. So you can only read it once when the flag is 0. You can't keep reading it because you've lost it after the first time you read it. So this will all become a little clearer as we do an example. Let's talk about the SPI registers. So there are 2 SPI ports on our chip at these different base addresses. Key registers are that baud rate register, the clock mode register, transmit data, and receive. So the baud rate register, the bottom 12 bits indicate the clock divisor, and the frequency of the SPI clock is the frequency of a core clock divided by 2 times 1 plus the divisor. So if we set div to 15, div plus 1 is 16, 16 times 2 is 32, so fs clock equals 16 megahertz over 32 equals 0.5 megahertz, which is a fairly safe speed for transmitting even with lousy breadboard wiring. Clock mode, if we wanted to set the phase and polarity, we do that in the bottom 2 bits. Transmit data register, first we look at bit 31 to see if it's full. Once it's not full, we write to bits 7 through 0 to transmit data. Similarly for the receive data, we look at bit 31 to see when it's empty. As long as it's empty, we keep reading it. Once it becomes not empty, once the empty bit is 0, then there's data waiting for us, and we find it in the bottom 8 bits. So let's write a library to do SPI in our device driver. So first we need to define these registers. Here are, from the data sheet, the registers we just talked about. For instance, the S-clock divider has 12-bit divisor field, and here we can declare a structure called S-clock div bits that has a 12-bit field indicating the divisor. So the syntax of this structure, this is called bit fields, and the overall register is 32 bits, uint 32. But of those 32 bits, 12 bits, the bottom 12 bits indicate the divisor, the next 20 are unused. Similarly, we could declare the bits for the S-clock mode register. The bottom bit is the phase, the next bit is the polarity, and the upper 30 bits are unused. For the transmit data register, the bottom 8 bits are the data, the next 23 bits are unused, and the top bit is the full flag. And the same thing with the RX data. So now we've defined different data types for each of these different registers. This is somewhat different than GPIO, where each register just had 32 bits to control 32 different GPIOs. Now we can declare a structure for the overall SPI memory mapped I/O. So at an offset of 0 is the S-clock div. So the first thing in the structure will be S-clock div, and it will be of type S-clock div bits, which is what we defined up here with 12 bits for the divisor. Next will be S-clock mode. It's right here, an offset of 4, and that was of type S-clock mode bits, with 2 bits specifying the phase and polarity, the other 32 unused. Now, the next 2 locations in the memory map are just unused. So to specify that in our structure, we can have an array of 2 uint32s, 2 4-byte numbers, and we'll call them reserved. That means that later the manufacturer might add some more registers to the system, but right now there's nothing at that address. Then we have a register for the chip select ID, register for chip select default, chip select mode. Those are ones we haven't talked about, and usually they're okay by default. There's some delay registers that we usually don't have to deal with. A frame format we'll ignore for now. But then we get to the good stuff, transmit data and receive data registers, which were of type TX data bits and RX data bits. And those now are an offset of 4, 8, and 4C. So the 4 most interesting registers to us are the ones underlined here. But as you see, SPI has a variety of other registers that could be used for configuration. So now let's put together our library. So we need to define the base address. This is for the QSPI used for the memory interface. We probably won't use that one. SPI1 starts at 1002 4000, and SPI2 at 1003 4000. And then we'll set up some pointers. Both are pointers to an SPI structure at these base addresses. All right, so now before we could use the SPI, we need to initialize it. Let's have an initialization function that takes the clock divisor, the phase, and the polarity, and sets that all up. So we begin by calling the pin mode function, and we'll set pins 2, 3, and 4 for the SPI, all to IO function 0 to use them for SPI. Then we'll configure some of the SPI control registers. Remember, we can dereference that pointer to our SPI1, look at the S-clock div, go into the div field, that 12-bit field with the clock divisor, and put in clock divide. Same way with bit 0 and bit 1 of S-clock mode, we'll put in the polarity and the phase. Now here's a function that will send 8 bits and receive 8 bits back. So the first thing we need to do is look at the TX data register, see if it's full. As long as it is, we just wait. Once we leave this while loop, the transmit data register has room in it, so we can write to the TX data field with the value to send. And the nice thing about these bit fields is C does all the work to change just those bottom 8 bits of the register without touching the other bits. Now, to receive data back, we're going to need to wait until the received data is not empty and then look at the data field. But the trick is, once there's data, we can only read it once, and the act of reading the data also clears it out. So we'll do a loop, and we will read the SPI Rx data field. We'll look at the empty field. If it's not empty, then we got something good, so we want to return the 8-bit data field. Otherwise, there was nothing in the Rx data, so we go back to the while loop and we keep reading the register until it's no longer empty. Now let's talk about generalizing the pin mode function. Previously our pin mode had handled input and output, but now we want it to be able to handle a GPIO IO function 0. And you might remember for IO function 0, we need to set the IO function enable bit for that GPIO, and also set the IO function select to 0 for function 0, or to 1 for function 1. So we can define 2 new modes. In addition to input and output, we now have IO function 0 and IO function 1, and pin mode can put us in any of those. Alright, so now let's write a little program to do some SPI communication. We needed to include stdint to get our data types, and the EasyRed5IO. And then in our main function, let's declare an 8-bit integer for the value we're sampling from SPI. We'll initialize the SPI at 500 kilohertz, phase and polarity being 0, and then repeatedly let's send a message of 60, which is 01100000, and then we'll send another message of all zeros, and we'll get back 8 bits. We'll store them in the sample register, and maybe we could print what we received and wait. So this would keep sending messages and getting back value.